Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on complex analysis, lecture number 15, in which I will solve some more problems on analytic function. Now we solve a problem number A of 1, so that second order partial derivative with respect to x plus second order partial derivative with respect to y equal to 4 multiply second order partial derivative with respect to z and z bar. These are operators. Now we solve this. Since z equal to x plus iy implies that conjugate of z equal to x minus iy, adding, this is number 1, this is number 2, 1 and 2, we get z plus conjugate of z bar equal to 2x, implies that x equal to half z plus z bar, that this is number 3. Now subtracting 2 from 1, we get z minus z bar equal to 2iy, implies that y equal to 1 by 2i z minus z bar. This is number 4. From 3, if we differentiate this with respect to z and z bar respectively, we get partial derivative of x with respect to z equal to half partial derivative of x with respect to z bar, this is also half, this is number 5, this is number 6. From 4, here partial derivative of y with respect to z equal to 1 by 2i, partial derivative of y with respect to z bar equal to minus 1 by 2i. This is 7, this is 8. Let phi be a function of xy. Therefore, partial derivative of phi with respect to z equal to partial derivative of phi with respect to x, partial derivative of x with respect to z plus partial derivative of phi with respect to y, partial derivative of y with respect to z. This is equal to del phi by del x. Here from 5, this is half, del phi by del y by del z, 1 by 2 I, using 5 and 7. This is equal to half del phi by del x, half common, plus 1 by I del phi by del y. This is equal to half del phi by del x plus 1 means minus I square by I del phi by del y. This is equal to half del phi by del x minus I del phi by del y. Implies that if we do not mention phi, we will get del by del z equal to half del by del x minus I del by del y. Let this is number 9. Now we differentiate partially both sides of this with respect to z bar. We get del phi by del z bar equal to del phi by del x by del z bar plus del phi by del y by del z bar. This is equal to del phi by del x by del z bar is half from 6 plus del phi by del y by del z bar minus 1 by 2I from 8 using 6 and 8. This is equal to half del phi by del x. We have taken half common, so here remains minus 1 by I del phi by del y. This is equal to half del phi by del x minus 1 means I square by I del phi by del y. This is equal to half del phi by del x plus I del phi by del y. If we do not mention phi both sides, we will get del by del z bar equal to half del by del x plus I del by del y. Let this is number 10. Multiplying operators of 9 and 10, we get del 2 by del z bar equal to 1 by 4. Here minus sign, here plus sign. Therefore, this will be equal to del 2 by del x square plus del 2 by del y square. Implies that 4 del 2 by del z bar equal to del 2 del x square plus del 2 del y square, and proved. Let this is number 11. Now we solve next problem. Next problem is b of 1. Prove that second order partial derivative with respect to x plus second order partial derivative with respect to y. This is under bracket. Modulus of fz square equal to 4 modulus of derivative of fz whole square. Now we solve this. Solution. Since modulus of fz square equal to fz multiply conjugate of fz, and this equal to fz multiply f conjugate of z. This is number 1. Since from 11 previous problem we know second order partial derivative with respect to x plus second order partial derivative with respect to y equal to 4 second order partial derivative with respect to z and z bar, implies that del 2 by del x square plus del 2 by del y square modulus of fz square equal to 4 del 2 by del z bar modulus of fz square, and this equal to 4 del 2 by del z bar using 1. This is fz multiply fz bar using 1, and this will be equal to 4 del by del z. We differentiate partially this with respect to z bar. We get fz same and derivative of fz bar. And this will be equal to 4. Now we differentiate this with respect to z partially. So this will be 4 f prime z derivative of fz multiply f prime this z, here we may write conjugate. So this will be equal to 4 modulus of f prime z whole square. We know that f z conjugate equal to f conjugate z. Similarly here f prime conjugate z equal to conjugate of f prime z, and this proved. Now we solve next problem. Problem A of 2. Problem is if function of z equal to u plus iv is an analytic function of z equal to x plus iy, and let phi be any function of x and y with differential coefficient of first and second order, then partial derivative of phi with respect to x whole square plus partial derivative of phi with respect to y whole square equal to bracket curly bracket partial derivative of phi with respect to u whole square plus partial derivative of phi with respect to v whole square curly bracket closed modulus of derivative of fz whole square. Now we solve this. Given that fz equal to u plus iv is an analytic function of z equal to x plus iy. Therefore, by CR equation, Cauchy-Riemann equation, ux equal to vy and uy equal to minus vx. This means partial derivative of u with respect to x equal to partial derivative of v with respect to y and partial derivative of u with respect to y equal to minus partial derivative of v with respect to x. Let this is number 1 and this is number 2. Let phi is a function of uv where u is the function of xy and v is the function of xy. And this is number 3. Therefore, partial derivative of phi with respect to x equal to partial derivative of phi with respect to u multiply partial derivative of u with respect to x plus partial derivative of phi with respect to v multiply partial derivative of v with respect to x. This is number 4. Again, from 3, partial derivative of phi with respect to y equal to partial derivative of phi with respect to u first, and partial derivative of u with respect to y plus partial derivative of phi with respect to v multiply partial derivative of v with respect to y. This equal to, since uy equal to minus vx, from 2 we may write this del phi by del u multiply minus del v by del x plus del phi by del v, vy is ux multiply del u by del x. This is number 5. Squaring 4 and 5 and then adding, we get left side is del phi by del x whole square plus del phi by del y whole square. Right side will be this square plus this square plus 2 into this multiply this. This will be positive, and here this square plus this square minus 2 into this and this, and to multiply this and this will be cancelled. So we write del phi by del u whole square multiply del u by del x whole square plus del phi by del v whole square del v by del x whole square plus del phi by del u whole square del v by del x whole square plus del phi by del v whole square del u by del x whole square and this will be equal to, here we take del u by del x whole square common from this and from this. Del u by del x whole square common remains here del phi by del u whole square plus here remains del phi by del v whole square plus we take common del v by del x whole square from this term and this term. Del v by del x whole square remains del phi by del u whole square plus del phi by del v whole square. So we take common this term from both. This equal to del phi by del u whole square plus del phi by del v whole square. Here remains del u by del x whole square plus del v by del x whole square. Let this is number 6. Since we know that derivative of fz, f prime z equal to ux plus I vx, that is del u by del x plus I del v by del x. Taking conjugate a prime z conjugate, this equal to del u by del x minus I del v by del x. Let this is 7, this is 8. Multiplying implies that f prime z multiply f prime z conjugate equal to here del u by del x whole square plus del v by del x whole square. If we multiply 7 and 8 right side, we will get this, and this will be modulus of a prime z whole square equal to del u by del x whole square plus del v by del x whole square. This is number 9. Here left side is del phi by del x whole square plus del phi by del y whole square. Here using 9 in 6 we get del phi by del x whole square plus del phi by del y whole square equal to del phi by del u whole square plus del phi by del v whole square. Multiply. Value of this is modulus of f prime z whole square. This is number 10. Proved. Now we solve the next problem. Problem is b of 2. Here we have to prove second order partial derivative of phi with respect to x plus second order partial derivative of phi with respect to y equal to under bracket second order partial derivative of phi with respect to u plus second order partial derivative of phi with respect to v multiply modulus of derivative of fz whole square. Now we prove this. Since from previous problem we have del phi by del x equal to del phi by del u by del x plus del phi by del v by del x and del phi by del y equal to minus del phi by del u del v by del x plus del phi by del v del u by del x. We may write this as del by del x. We remove phi and make it operator equal to del u by del x del by del u. First we write this and we remove phi plus del v by del x del by del v. We remove phi. This is number 1. Similarly here del by del y equal to del minus del v by del x del by del u plus del u by del x del by del v. This is number 2. Implies that del by del x plus I del by del y. This equal to, we multiply second by I. Firstly we write del u by del x del by del u plus del v by del x del by del v minus I del v by del x del by del u plus I del u by del x del by del v. We take common del by del u. Here del by del u, here del by del u. So we get del u by del x minus I del v by del x. Common is del by del u. Plus we take common I del by del v. Firstly write I. If we take common del by del v, here del u by del x, here del by del v. So we may write here minus I del v by del x. I multiply by I square minus 1 minus minus plus, here plus. Multiply del by del v. This is number 3. Implies that del by del x plus I del by del y. Right side this common. Del u by del x minus I del v by del x. Here remains del by del u and here I del by del v. This is number 3. Similar to 3, we may write del by del x minus I del by del y. Here del by del x minus I del by del y using 1 and 2 left side equal to del u by del x plus I del v by del x multiply del by del u minus I del by del v. This is number 4. Multiplying 3 and 4, we get del 2 by del x square plus del 2 by del y square. This equal to here minus here plus. So del u by del x whole square plus del v by del x whole square. Here plus, here minus. So del 2 by del u square plus del 2 by del v square. We may write this as del 2 by del u square plus del 2 by del v square. Multiply del u by del x whole square plus del v by del x whole square. This is number 5. Since fz equal to u plus iv is an analytic function, therefore derivative of fz equal to ux plus I vx implies that conjugate of this equal to ux minus I vx multiplying f prime z multiply f prime z conjugate equal to ux square plus vx square, and this is equal to del u by del x whole square plus del v by del x whole square. Implies that this means modulus of f prime z whole square. Since we know modulus of z square equal to z bar, and right side equal to del u by del x whole square plus del v by del x whole square. This is number 6. Using 6 in 5, we get left side del 2 by del x square plus del 2 by del y square, right side del 2 by del u square plus del 2 by del v square, and value of this is modulus of f dash z f prime z whole square. Now inserting phi in both sides, we get del 2 phi by del x square plus del 2 phi by del y square equal to del 2 phi by del u square plus del 2 phi by del v square multiply modulus of derivative of fz whole square. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.